Hello everybody and welcome back to Environmental Science 101. This week we do water, right? So we had air, earth, water. What's the pattern? Nobody knows. Awesome. So what are we trying to do? Describe the water cycle and relate it to other things we have talked about. Climate, nutrient flows. Awesome. We'll look at the key chemistries and reactions and parameters of water. If you've ever taken a strip, all right, one of those test strips and tested fish water, then you already know everything. So good. It'll be easy. Awesome. We'll look at ecosystems right now. These are all going to be water-based ecosystems, but there are some water-based ecosystems on land and some in the ocean, right? You'll see what I mean. And then finally, we look at pollution and contamination of water, all the different ways it can happen, and the effects on human beings. Awesome. So let's get right to it. 4 sections: water cycle, chemistry, ecosystems, and pollution. Cool. First is our hydrologic cycle. Image here of flooding in Pakistan recently. Not good. These are power lines. Okay. Awesome. So Earth's water overall, right? So Earth, as we might remember, is about 70-75% water. Human beings, it varies anywhere from 50 to 80%, depending on their age and other factors, right? But these are roughly the same. Is a good way to remember it. We can take a look, right? So this is all the water in the entire world. Vast majority of this is going to be in the oceans, right? We've got about 2.5% that's going to be fresh water. Now, of that 2.5%, right, there's already a tiny fraction. Most of it is going to be locked up in glaciers, right? Things like Antarctica, Greenland, big ice sheets, or other glaciers elsewhere, right? About a third of it is going to be groundwater, which we'll talk about. And then only 1% of the 2.5% is actual fresh water, right? Now, maybe 2/3 of this groundwater is unavailable for human use. Maybe about a third of this 30% is actually usable to human beings. So we're whittling it down. And of that surface and other fresh water, right? A lot of it is going to be in ground ice and permafrost form, which is inaccessible to human beings, right? And then it's only going to be a little bit of that is in lakes, rivers, living things, the atmosphere, right? So we're talking about a tiny fraction of a fraction of a fraction of a fraction of a percent of all the water on Earth that is going to hold on to a lot of life, and that's going to be extremely important for us as human beings, just to put it into perspective, right? So we're going to talk about the water cycle, right? We might have learned one version of this a long time ago. It's very common. We're going to take that and then add some stuff on to it, right? Kind of complete it. So this is a cycle that doesn't have a start or end, right? It just keeps going. Things move between these different parts of it. It's ultimately driven by energy from the sun, which is going to lead to our sort of starting point, right? And as far as how quickly these things move, broadly speaking, we don't have to worry about that much, but keep in mind, so when we're underground, right, in the groundwater world, it can take a long time. I mean, it can take thousands or even tens of thousands of years for water to move from one place to another. And so groundwater resources, when they're extracted, do not necessarily replenish at the rate that you would expect compared to something like a lake, right? Awesome. So before we get to evaporation, we have to talk about changing states of matter. This is going to be a review, right? But we have solids, right, packed together, touch each other, liquids, which are moving around somewhat, and then gas, which move all over the place. Melting, right, and evaporation are going to be going from solid to liquid, and then liquid to gas. Condensation, right, condensing, and then freezing. Then sublimation is where we jump directly from solid to gas, or deposition directly from gas to solid. This one we don't care about too much. This is mostly going to happen in settings like at the tops of mountains, where snow will sublimate or come back. Awesome. Cool. So evaporation is going to be our starting point. So we said there's no beginning or end on the water cycle, but this is the best mental starting point, right? So sun hits water in the ocean and evaporates it. And it evaporates, right? And it's going to move elsewhere from there. This is going to be moved onto land, where it is going to precipitate, right? But I want to talk about evaporation and transpiration together, right? As these two processes that take water and put it into the atmosphere. And a lot of times, even though we're talking about the ocean here, on land, evaporation and transpiration are basically the same. Like, you cannot separate one from the other in a land setting because plants are just part of it, right? So this is basically plant sweating, all right? Plants are always taking in water, and they got to release it at the same time. Long story short, we might remember gas exchange through the stoma or stomata. We might also remember that water is required for photosynthesis, right? So we take it in, we use it, but we have it constantly flowing through the body. We got to get it out somehow. This is transpiration. Going to be a lot of what returns water up into the atmosphere, especially on land. And we return it to the atmosphere, it comes back as precipitation, right? One of our major parts of climate, along with temperature. Sunlight can take many forms, right? Rain and snow especially, though rain is what we're going to be the most concerned about. This has a big influence on all these other factors, right? Amount of precipitation determines the quality of the soil, which determines its richness and how suitable it is for plants, which determines which animals can live there and so on. Okay, this is a major factor that is going to influence biodiversity. Precipitation is going to be important for life everywhere. Typically, this is measured in something like centimeters or inches per year, and you can maybe quiz yourself here. See if you know how much rain Phoenix gets in a year. Awesome. This is a precipitation map of the United States, right? And as we can see, right, this is, inches per year, average annual precipitation in inches. There's lots that we could talk about here, but more than anything else, right? So 25-ish is about the threshold that you need in terms of average annual precip to be able to grow crops without having to irrigate, right? And having to build dams and do all these other major projects, right? So we can see extremely clearly, right? If we were to go back, right, to 18th, 19th century, right? This was a really hard dividing line between land that you could farm, right, and the West, right, which had to be conquered, had to be, rivers dammed up, irrigated. Now, later, we'll get into problems with irrigation and how it's kind of a losing battle, right? But that's the essence of it. And then those of us here in Arizona, it's maybe even more sorry than it appears, but we would be in this category here, right? Something like 10 to 12 inches of rain per year for those of us in the valley. It's concentrated in the monsoon season, not in the winter, as opposed to some of the other deserts who kind of get it in the winter as well. Right, we've got evaporating water, right? It comes up, comes down in the form of precipitation, and, right, when it hits the ground, does it disappear? No. Some of it is taken up by plants, right? But a lot of it is going to infiltrate, is the word, down into the groundwater system, okay? And we can kind of use our imaginations here. So you can imagine being outside, right? And you dig a hole down into the ground and you just keep going and going and going and going and going. Sooner or later, you will hit water. In fact, you're going to hit a water level that kind of stays constant even as you try to dig the hole deeper. And it's going to be tough, right? So the water, right, that's filled up in there, that is groundwater. And you have hit this thing called the water table. The terminology here is really not important at all, right? What's important is for us to understand that there is this big pool of groundwater, that the groundwater itself, pool is maybe not the right word, right? It is going to be in these little cracks in fractured rock, or it's going to be in those like little holes, right, between soil particles. So we talked about how soil is about 25% air, 25% water, right? And then, 45% minerals. Well, that's going to be our groundwater, right? Here in Arizona, groundwater is extremely deep. Other places, not so much, but here, 100, 200, 300 feet down to get to groundwater. Very few plants are able to reach that. Awesome. So just to kind of put it in perspective here, right, this is like a river or a lake, right? And we notice that the surface water level, right, extends into the ground where it becomes the water table. These are one and the same. If we were to drain this, water would come out of the ground and start to fill it in. And vice versa. If we have a bunch of rain here, it's going to infiltrate into the ground. And that's what we have to know for now. So, yeah, we have covered this in the previous one. Awesome. Okay, so some of the water coming down from precip, right, is going to infiltrate. Some of it is going to stay on the surface and start flowing. Now, it's pretty rare that this happens in sheets, but it does happen. We might recall that this is a process that takes fertilizer away from farms and into the ocean through streams and is not good, right? Rains, water enters the ground, right? Some of it infiltrates down to the ground, some of it enters rivers, but some of it doesn't do either of those and just moves over the land, not in river form. That is your surface runoff, right? Whenever we have flash floods here in the desert, so relatedly, our extremely dry and typically sandy soils can't really absorb water that comes down, at least not very quickly, right? So the reason why we get flash flooding is because when we have a rainstorm event, which tend to be concentrated in certain months out of the year, right? Concentrated, lots of precip in a short amount of time, can't infiltrate into the dry soil. And so what does it do? It piles up on the surface and flows in these sheets. It can be very dangerous. Relatedly, okay, so when we talked about infiltration, right, getting into the soil, right, well, let's ignore the things on this picture, right? Let's imagine that these people had a well, right? It's like a big hole that goes all the way down into the groundwater, and they're pumping water out constantly, over and over and over and over and over, as people do with wells. As we pump water out of there, the soil, right, above the water gets smushed down, is the easiest way to think of it. And as a result, you have subsidence, right? Where the level of the land, we can see, right? So this is where the land level was in 1969, right? Here it is in 2018. It has fallen a lot, right? So this person is, I don't know, 6 feet tall, right? So that's 12 feet. This is a lot, all right? It affects Arizona, and this could happen not just in a little patch of land, but over tens, hundreds of square miles. They can all drop by a lot, right? Another example here is in California, the San Joaquin Valley, extremely bad, right? So here's where it was in 1965. Here's where it is in 2016. No joke, the ground has literally sank that far because groundwater has been pumped out excessively. It's really a problem, right? And whoever pumped out the groundwater, are they the ones who pay the costs now that it's down? No. All right, we got issues with this. Sinkholes, relatedly. Okay, so just to clarify, because this can be something that is scary for students in some instances. So a sinkhole like this cannot open up here in Arizona, in the streets, in your home. It cannot happen here. So this is in, I believe, Nicaragua. I'll put it in a note. Anyway, they had pipes running up through here, right? Leaky city pipes that were not well maintained, not inspected, not taken care of. They leak and it creates this big hole like down here under the surface for a long time, right? Until the hole under the surface gets so big that this stuff collapses down. And that's exactly what happened here. Now you can get sinkholes, and lots of them in certain parts of the country, right? Virginia all the way down through Florida especially can be bad. Stories all over the place of people whose homes have fallen down into sinkholes in Florida. It can be really hard to find these things. A lot of underground work that gets done trying to find them, entire developments where they figure out after they build all these houses that there's sinkholes, and then it's a catastrophic issue. Not good. All right. So to put it all together, right? We talked about how water evaporates in the ocean, right? Condenses into rain and moves around, right? Some fraction of it, well, okay. A lot of it is just going to rain back down into the ocean, but some part of it is going to come onto the continents, right? And rain down. We don't really worry about sublimation up the mountains or deposition down as snow. This would be if we did a unit on glaciers or something, right? We're going to think about precipitation coming down, right? It's absorbed into the ground, right? Some of it through the groundwater, some of it runs off on the surface, some of it gets channeled into rivers, some of it gets taken up by plants, right? Have a lot of evaporation that happens here, and the evaporation that happens on land cannot really be separated from the activity of plants. It's just so important, which sweat and transpire and put it back. And there we have our water cycle. So next we'll do chemistry.